So this is lecture 7 of linear regression with regularization module 3. And this is a extra module and the cover the contents we don't have time to cover during class. So this module focuses on the geometric interpretations of ridge regression and lasso regression. And I reuse part of my last year's recordings on those kind of geometric interpretations. The reason why I borrowed those old recordings is because I think the geometric views is extremely important and helpful to understand the intuitions of ridge regression and lasso. All right, so let's get started.
Ordinal least square solutions like a bell, right? In this, when you have two x and one j theta, two different theta 0, theta 1, you really have some kind of bow shape, right? So this is the surface map, this is the contour map. In the contour map, you really just go from a random start and go slowly, a little bit, according to the gradient direction, goes to the center. And that center solution is your, in our case, in this case, we call that beta ordinal least square solution. And this is the contour map if you show in the 3D view and the surface map. So in the surface map, and we actually print out our training error, right? If you think about what is training error, the whole training error is really just this curve. For every theta you calculate that loss. And that loss keeps decreasing until the minimal you reached. And that's exactly that fitting training error versus the epoch you're trying to plot. And this is on the contour map, it just looks, because contour map in the end is the movement of your theta vector. And the surface map is the changes of the objective function. Questions? So, okay, so now I have this solution. What does this even mean? I'm adding that beta transpose beta, right? So let's come back to see this. I'm trying to look for a minimal solution with this bow shape of the loss function. At the same time, I want to make sure my beta vector is the summation of that quadratic form is within S quadratic. Okay, so it kind of tells me what is the contour map of this. Summation of every element and then quadratic is smaller than S quadratic. This is exactly a circle centered at the origin point. And the size of the circle is S. Because every point within the circle satisfies summation of beta I. Let's come back to see this. Is here. The summation of beta, each element's quadratic summation is smaller than S quadratic, which means you can only have solution of those points within the circle. Okay, now I have two goals, right? I want to have on the contour map to be as close as that center, that oval-shaped center, but I need to satisfy the other criterion is the point has to be within this blue circle too. And this is exactly what ridge regression is doing. We have two goals, we want to satisfy both. And that type of solution is whatever point on the boundary of here, it's almost the, and here hopefully it is at the minimum point it can reach in terms of that bow shape, because the inner, the loss function is lower, right? The outer, the loss function is higher. Of course, this point compared to every point here has a lower loss for that sum of square error loss. hope this is another figure like this. So this is a 3D view. So in the end, I have like a bell shape about my sum of error laws. The lower in the bows, in the middle, the smaller of the sum of square error. But at the same time, I have a cylinder constraint. That cylinder constraint constrain all my points has to be within that cylinder. And then this is really just a cylinder, and so there's a cylinder here, and then there's a bowl shape. The higher the loss, the lower, the smaller of the sum of error. There has to be a touch point, right? And that touch point is the solution of ridge regression. It satisfies both. It's within the circle. At the same time, it's compared to all the points in the circle, its loss is the smallest in the sum of squared error loss. I can find a perfect cylinder and then a bowl shape, and the bowl just kind of cut through the cylinder. So the true thing actually is like the bell shape cut through the cylinder, right? If you think about it, again, the solution is I want it to be small, but at the same time, I want the points to be within the S circles. So I have to look for the solution has to be the points within the circle. Every point within the circle satisfy that property, right? Beta transpose beta smaller than S squared. So every point, all the blue points satisfy that properties. Its solution has to be one of these points. And at the same time, I want to minimize the sum of squared error. And if you see the contour map, the more closer to here, the smaller orders of the loss. Of course, there's other loss functions, other contour, look like this, right? And the contour just shows the 3D, actually 2D view of the loss function. And if you compare the solution of this, of course, this is the best solution because this is the closest to this ordinal least square solution. At the same time, it satisfies the circle requirements. And when you have just think about a random, we do equation based or gradient descent based, you can't draw that gradient because the gradient is a little bit shaky. So you need to start from here. Some random points start here because you have to. This is the requirements. In mind, it's S for now. And I'm going to discuss with you what is the relationship of S and lambda in a few slides. And there's an analytics relationship of S and lambda. And just keep in mind, when you do gradients, in this case, you have to within this circle. And there's no way you move out because that's just requirement. And this is your solution path, speculated. But no matter how you move, you need to within your circle because that's a requirement. It's related to lambda. So I motivated the whole thing through one is not invertible. But in fact, ridge regression is a very good solution even if it's invertible. All right, so we call this solution as a ridge regression solution. We call this solution as ordinal least square solution. And so, so that's the equation. And this is the 3D view. And I hope next time I can find a better 3D realization of this. So influence of the regularization parameter. So we already said, and this is S, right? And so when I'm increasing S, I'm increasing this blue circles, right? The blue circle really large. What is it? When blue circle really large. Blue circle so large, it will cover this. Yeah. So that's this. When S got really large, it's equivalent to lambda close to 0, which means there's almost no regularization. Your solution will be the OLS solution. And so this is S really large. And when the lambda goes to infinity, your S is really small, very, very small. S is very small, which means what? Your solution will vary off, actually absolutely off a lot, if your OLS solution is very far from the origin. You penalize a lot. The whole penalization dominates the solution. Question. So your question is, can I reformulate it? How do you pick lambda?
How do you know if you picked a bad one?
Good question. So it's related to how do you pick up lambda. So this is a very important hyperparameter in this type of regularized regression, and it's almost similar to in the polynomial regression, what D do you pick? How flexible do you pick? But in this case, it's about how much regularization you added on the whole solution. Again, I'm going to talk about it. So there's regularization path, but in the end, still people use cross-validation to pick the right lambda. Questions? So when lambda is so large, the regularization dominates, and your solution will be pretty off, because very clear from that figure, right? You're not going to go all the path, you're going to stop at the boundary of the circle or the sphere. If S is so large, S is so large, lambda is so small, and the regularization almost has not much influence at all. Okay, so that's the summary, and then let's talk about next. I already talked about subject to a circle or a sphere. And then you can have all the other variation of shape, right? Why the circle? You can have a diamond. And this is exactly that diamond solution. So rather than summation of beta j quadratic smaller than s quadratic, that's really the sphere or quadratic, the circle geometric representation. Now we're just constrained by summation of the values of the elements smaller than a number. So now we change to absolute value. We talked about it geometrically. This is it. You can actually prove it very easily. So the boundary of that is the L1 norm. The boundary of L1 norm are the lines, all these points. So this gives you a simplex type of shape. And in the 2D case, this is actually just a diamond. And you can actually very easily just B1, beta 1 plus beta 2 equals to that constant S, and this is my boundary, and this is that line, right? And this line, and this line. And this create a boundary plane. And you have to, within this, and then look for the points, minimize the sum of square area, at the same time considering that the bell shape of the walls, the surface map, and normally there's a good property. So let's just assume, you move here, here, and here. So there's a good property is there's a highly likely good chance this kind of corner shape will touches the corner with your bell surface map. The corner means what? In this case, the corner point means S0, right? this point actually pushes the beta 1 to be 0, and beta 2 has a quantity. So this type of solution will give my beta 1 equal to 0. And when you have a lot of dimensions, it will push quite a number of beta j equals to 0. When you look at your weight vectors, what you learned, and you're going to get your beta lasso will be some kind of vector with a lot of zeros. Some kind of numbers or maybe whatever. So this what we mean it's a sparse vector with certain level of sparsity. Okay, so again, sparse vector because a lot of the entries are 0. Okay, so why is this good? So when you have a lot of coefficients being pushed to 0, and when you perform that y equals to x transposition beta, it's equivalent to I'm removing a lot of feature out. Essentially, I'm selecting features through the solution by not performing explicit feature selection at all. And I get a simpler model and hopefully a more interpretable model. And this is normally called Sparse Solution. So this is a lasso solution, this is the S solution. Questions, I hope the ridge regression discussion already resolved all the confusions about 3D. And it's actually very difficult to geometrically show this type of shape. It's easily not this part touches, is the best point position touches that contour. It's normally highly likely it's a lot of corner points touches the contour. And there are a lot of discussion online, feel free to read those. It's about the property of the loss function. And I think I don't have a 3D view about this because it's so hard for me to visualize. Let's compare ridge solution versus a lasso solution versus a ridge solution. So we already talked, we already derived. Ridge solution has the shrinkage. It's really shrink, right? This figure almost, I'm shrinking the beta 1 to here. I'm shrinking that beta 2 to here. There's a shrinkage effect, but it doesn't shrink to 0. But lasso is also shrinking, but the shrinking is a little bit different. It shrinking a lot of those beta into 0. One is a soft shrinkage. The lasso is a hard shrinkage. All right. All this formulation share the same formula. Error on the data plus regularization. So in the end, if you summarize this whole category of approach is to revise the loss function by adding regularization constraints. And of course, I mean, not just beta 1 or L1 or L2, you can have the Q norms, right? You actually can have all the variations like we showed before, Q equal to 4, Q equal to 0.5, Q equal to 0.1. So again, this is the contour map, right? This is the contour map of the norm function. Whatever in those blue regions share the same norm, Q norm, which is in this case 0.1 norm. So what we had used so far is all here. The reason is this one smaller than 1, the norm function is not convex formulation anymore, which is extremely undesired properties people used to think. because when it's non-convex, right, it's very difficult to actually optimize to guarantee the convergence properties. So in the end, most actually all the regularized version is using the norm here, larger than 1. And yeah, so yeah, so there's even, you can even go even more, right? So 2, 3, 6 inf. And when it reaches inf, the contour map changes from the oval shape into a square. And if you think about it, and what is that? So this actually means this is the inf norm, right? Inf norm means the max. 1, so when we have x2 larger than x1, we have all this output of the norm as the x2. When we have x1 larger than x2, we have all the output as, so this is the boundary point. And you can actually tell this properties of inf norm versus other Q norms.